Assalamu alaikum. Welcome to my channel M.Asif Math Corner. Today we will discuss about two important theorems related to subgroups. Let's come to the lecture. The first theorem is a non-empty subset H of a group G is a subgroup of G if and only if for any pair AB, A comma B belongs to H and AB inverse also belongs to H, where A is not equal to B and A and B both not equal to E. E means identity element. It's mean that A is not identity element, B is not identity element, and A and B are not same. Let's come to the proof. Suppose that H is a subgroup. If and only if means that we have to prove the theorems in two ways. The first way, we said that it is a subgroup and we prove that it is closed, and in the second way we suppose that it is a closed and prove that it is a subgroup. Let's start. Suppose that H is a subgroup of G. In first we are going to prove that it is a closed set if it is a subgroup. So suppose that H is a subgroup of G, so H static is a group because G is group under static under the given binary operator static. Therefore, if H is a subgroup, then if B is belongs to H, then there exists B inverse and belongs to H also because H is a subgroup. This implies that A comma B inverse belongs to H and AB inverse belongs to H, which proves that it is closure property hold. Hence, in second way, conversely, we are going to prove that if it is closed, then it is if H is closed, then H is a subgroup. Suppose that for A comma B belongs to H and AB inverse belongs to H, we are going to prove that H is a subgroup. Now put B is equal to A. According to the given condition, in the place of B, we put A. We put B is equal to A. So A comma A belongs to H. This implies that AB inverse, A inverse, because at the place of B, we put A. So A inverse belongs to H, and we know that if any element multiply or operate by its inverse, it gives us identity element. So one condition is proved that identity element is present, exists in H. In H. Identity element is present in H. Now let E comma B belongs to H. This implies that EB inverse belongs to H. This implies that EB inverse means we are following the given condition, which implies that EB inverse belongs to H. And if identity element belongs to any element or inverse, it gives us that element or that inverse. It means that B inverse belongs to H. Hence inverses are also present in H. The second condition hold, and this implies that inverse. Again, let A comma B belongs to H. This implies that AB inverse, because inverses are present in H, belongs to H, which implies that A, and if B has inverse B inverse, then B inverse also has its inverse, that is also B. So AB inverse belongs to H, and inverse of inverse becomes that same element. AB belongs to H, which proves the closure law. The third property hold. Thus it is closed. The first, we prove that identity is present. Second, we prove that inverse is present. And in third, we prove that closure law. The given H is closed, the given set is closed under algebraic operation, and we know that in commonly associative law holds in every set we discuss. So associative law holds in H as it holds in G, therefore H is a group, hence proved. Let's come to the second theorem. The second theorem is show that prime Z prime has no proper subgroup. We discussed in earlier lecture what is proper subgroup. Proper subgroup is that if G itself is the subgroup of G which is called improper subset, and the identity element of the group G is trivial, and all other non-trivial subgroups are all proper subgroups. So he said that if Z prime show that Z prime has no proper subgroup. If P is prime number, we know that as the number of subgroup of Z prime is the same as the number of its distinct divisors. This is point to be understand. Distinct divisors. If any set, for example, contain 4 elements, if a group contains 4 elements, then its distinct divisors are 1, because the table of 1 is, on the 4 can be read, and 2, the table of 2 is also going on the 4. So 2 is the divisor of 4, 1 is the divisor of 4, and 4 itself is the divisor of 4. It means any group contain 4 elements that must have at least 3 subgroups, which contain 1 element. The second contain the 2 elements, and the third contain 4 elements, that is improper subset. So distinct divisors has a value. Distinct divisors are the subgroups, make the subgroups. That's why we know that on any prime number 3, start from 2, 2, 3, 5, 7, we know that prime numbers are 2, 3, 5, 7. What are prime numbers? The prime numbers are those on which those has no divisors rather than itself and 1. So distinct divisors of P we know that are only 1 and P itself. For example, P is 2, then divisor of 2 are 1 and 2. For example, P is 3, then the divisors of 3 are 1 and 3. For example, prime number, for example, the Z contains 5 elements. 5 is also prime number, 7 elements, 11, 13, 17, 19, 23, up to so on. These all numbers has only distinct divisor itself and 1. So the distinct divisor of P are 1 and P itself, and the number of distinct subgroup of ZP, here is ZP, are 1 and ZP itself, not ZP. ZP itself means Z prime or the subgroup of Z primes are 1 and Z prime itself only. No other subgroup it contains. Thus, the number of proper subgroups is 0. Why proper subgroup? We prove that Z prime contain only 2 subgroup, which is Z and 1 mean identity element, this and this. So we know that this is an improper subgroup, and identity is trivial subgroup, not proper subgroup. That's why it has no proper subgroup. So as we can say that ZP has no proper subgroup, we hence proved. We can say that Z prime has no proper. The proof ends here. I hope you understood. Please share my video and subscribe my channel, because your share has a value, as I told in our lecture. Your share has a value for that person who need it. So thank you so much.